We're now going to discuss the third and most prominent of the unsupervised learning algorithms, and this is around mixture models. And so I want to first point you to the book, the website, databookuw.com. All the code used here, both Python and MATLAB equivalents are there, as well as lots of other lectures around clustering and classification, as well as regression, neural nets, and a variety of data-driven science topics. So this, what we've talked about so far in unsupervised learning is k-means and hierarchical clustering, both very important, very easy to execute algorithms. The next one we want to talk about are mixture models. Now, mixture models are a really powerful tool for understanding how to do unsupervised clustering, and as it suggests, it's a mixture of models. What kind of models? Well, here everything's around a probability distribution, and so what you're going to do is think about data as being generated from different random processes, each with its own distribution, that are somehow mixed together to produce what is observed in the data. So what a mixture model tries to do is it's going to make an assumption about the form of the data. In particular, it's going to assume that it's a mixture of probability distributions. So your overall probability distribution, F here, which has some parametric dependencies, theta, okay, is going to be a sum, so you can add these together, of different probability distributions. There's k of them, so F of p, and there's k of these, is an individual distribution weighted by alpha of p, which helps make the entire probability distribution. Now you have to add up the alpha of p's in such a way that the overall probability distribution, the area in the curve, is 1, because it's a probability. But each individual distribution also has a probability distribution parameterized by its own parameters. And so your goal is pretty simple. Given some data, you're going to make an assumption about how many different probability distributions are there. Remember, just like as in k-means require you to make a choice about how many clusters there are. Hierarchical clustering also required you to give some kind of threshold or some kind of information about how many clusters you might want. This also is saying how many probability distributions do you think you need for that data. So that's determining k. And then what is the form of the distribution? So you're going to impose structure in the form of the model. Normally, a lot of times what we do is we make f of p be, in fact, a Gaussian distributed variable. And so what we would need to do then is simply determine what are the weights between the distributions, determine those alpha p, and determine the parameters of each of the distributions. And of course, we're going to do this through optimization. Remember, this is a regression problem, just like we talked about in chapter 4. I have input data, I have output data. This is the model. Right there. My model is a sum of distributions where I don't know the parameters of the distribution or their weights. Find those. That's the optimization problem, such that you best match the input to the output of the data. Okay? Now, what oftentimes happens is you assume that these f of p's, in fact, are Gaussians. Okay? Normally distributed variables, so in fact, Gaussian mixture models, GMMs, are kind of one of the important classes. If you have nothing better to guess about your distribution, you typically assume it's going to be normally distributed, right? Characterized by two numbers, a mean and a variance. There's no reason why you pick some kind of more complex or harder probability distribution unless you had information to why that choice should be made. So generically what people do, if you know nothing else, pick a normal distribution which has a parameterization by two parameters, a mean and a variance, which are things you can very easily compute for distributions as well. So your goal, given that, determine the weights, the variances, the means. So if I assume that this is a Gaussian distribution or normal distribution, then I have a mean and a variance for each one plus a weight. So 3 parameters I have to determine. So if I have a mixture of 2 Gaussians, then I have 6 total parameters I have to determine in order to get the best fit to the data. Okay, hopefully that makes sense. So the nice thing too about assuming that is it's a fairly well constrained optimization problem. There's a fixed number of parameters you have to determine through the optimization procedure. and in almost a minimal set of parameters, because one of the things that's nice about normal distributions is 2 parameters, all you need to characterize the whole thing. Okay, so we're actually going to do Gaussian mixtures here for some data that we're going to play with. This is the goal. Now, how do you actually do this optimization procedure? Well, there's a famous algorithm based upon maximum likelihood estimates. And the idea here then is to, just like I said, is you want to optimize this or minimize an error. So what typically is done is you take the derivative of the maximum likelihood with respect to the parameters and set it to 0. Okay, remember there is no maximum error. You can make your model fit as poorly as you want. In fact, you can make your model have infinity error. So if you get a minimum or a maximum of this derivative, it's going to be a minimum. That's the minimum that you can do, okay? So, and where L is a log likelihood function, which is the log of the probability distributions. Now, the reason you like to work with the log of the probability of the distributions is because the log of an exponential cancels out. So what you're left with is just something very simple, which is if you have a Gaussian, e to the minus x squared, then the log of e just gives you back the x squared. And then if you take the derivative of that, you get 2x. So this is sort of like your mean of that distribution can be easily computed in this log likelihood scenario. Okay, so this is what we're going to actually minimize. Now, one of the famous algorithms that was developed to do this was the expectation-maximization algorithm, or the EM algorithm. And it's going to make a number of assumptions, but it's basically an iterative procedures. And there's an E step and an M step. First is expectation, then it's the maximization. So if you remember in chapter 4, we talked a little bit about regressions, and we talked about alternating descent algorithms. And this is very much has the flavor of an alternating algorithm, where you first do one, then the other, and keep going back and forth. So what you're looking at here is a posterior distribution, or posterior estimates, which is you're going to take the normal. You're going to take some initial guess of the parameters. So you initially seed it randomly, typically, unless you have some information which will give you a better guess to start it with. And so what you do is you initially seed these distributions, and here's the overall distributions and the initial weights. So you're essentially guessing some distribution and their weights, and you're saying, what I'm going to do with this is I'm going to compute from every data their probability of which membership, which distribution they belong to, okay? So that's the idea. With an initial guess, this is very much like k-means, where you just start off with some guesses, and every point has to simply associate themselves with one of the cluster points, even though what you picked was completely random. Same thing here. I picked random distribution, a set of distributions, let's say Gaussian, with some random means and variances, and every point has to associate themselves with one of those distributions. And this is how you would do that. Now, once I've defined the membership for every single point, right, just like k-means, once I got that distribution, once I associate every point with one of the 2 points, I now said, let's find the center of mass of this new cluster that I randomly left and change my center point. Here, what we're going to do in the M step is, once you've done that, now you update the means, the variances based upon the membership that you actually generated from those initial guesses. So now you update the weights, the means, the variances. And here's these formulas for doing that. Okay, so I'm not going to go into detail of the expectation maximization algorithm. It's fairly standard, and you can work this out, and analytically. It's an optimization of that maximum likelihood estimate, but it's a nice alternating method where you first just pick some distributions, associate membership, now recompute means and variance according to that. Now do it again. Now take the data, all the data points, reassociate them with the distribution, find the new means and variances, and so forth until this converges. So you update your parameters and weights all the way until this thing converges, and that is your EM algorithm in practice, which actually finds for you these mixture models, or it defines how to get the parameters optimized for the mixture models. Okay, So I want to just highlight this on a couple data sets we've played around with so far. And what does it mean to do a mixture model? So for instance, in this one here, this is the real data. Now this is an unsupervised method, so I wouldn't know ahead of time what these were. So for instance, if I plotted all these just in gray without any labels, I might say there's a cluster here and there's a cluster here. So I'll just say this is Gaussian distribution, normal distribution here, normal distribution there. Go. Okay. Now what we know is that there's actually 3 here. So I might start off with picking 2 distributions, 2 normal distributions, so do a Gaussian mixture model with 2 distributions. But then I also could say, well, what happens if I did 3 with the hope that it would actually now pick up a distribution here, here, and here. So from the data itself, you can see it's not unreasonable to assume that there's some Gaussian distribution or normal distribution for these things. And so you would just say, I'll just assume it's true, put it in here, find me the best distributions that fit this data. Okay? Same thing here. For the dog and cat data that we've looked at, if we clustered around raw images and wavelet images of dogs and cats in some low dimensional space, right? Notice what we have here. What we have here is, if I want to do some clustering here, you might say there's a Gaussian here and there's a Gaussian there, or normal distribution in each, and you could say, okay, I will make 2 clusters and I will find the best 2 normal distributions that if I add them together produce the data that I see here. Okay? So right away you can start seeing that the structure you see in your data is actually what's motivating you imposing that there is in fact a probability distribution describing that data. Okay? Notice that this is very different than k-means and hierarchical clustering. In those, there really was no optimization. It was just simply execute an algorithm straightforward. Here, this E&M algorithm is trying to find you a probability distribution or approximate a probability distribution. There, in k-means and hierarchical, it's just simply cut it through, tell me where the data belongs. Okay, so the idea here is once you have that, you can start thinking about, I now can build classifiers out of that data in an unsupervised way because I have the probability distributions of the various components that's making up the data I see. Okay, and it's an assumption. So if you have 2 clusters, the idea would be there's probably 2 probability distributions describing those clusters that if I add them together, it will describe the overall data set. If there's 3 clusters, you might think about 3 probability distributions that would describe that data set. You have to pick the number of probability distributions to put in. So just like k-means, you got to pick the number of clusters. Here, you have to pick the number of probability distributions. All right, so let's go through some code. I'm going to show you how this actually looks in practice. We'll run through a Gaussian mixture model code. It's very simple to implement in MATLAB or scikit-learn or any of these. Very powerful. Okay. We are going to start back at the cat and dog data. So first of all, here it is. Load cat data in the wavelet domain, dog data in the wavelet domain. Remember that in the wavelet domain it was much more distinguishable about whether you have a cat and dog. So I'm going to take the dog data, cat data, concatenate them, and project it into a low-rank subspace by doing the SVD. Okay, so I take the data, I do the projection. We've already done this in the first lecture of this chapter, section 5.1. So I'm just playing out from there again. So I can plot all that, and this is what this is doing here. And now what I want to do is say, okay, let's come to here. In particular, one of the things that happened is when we projected, and this was from lecture 5.1, but I'll highlight it here, when we actually projected onto modes 2 and 4 specifically, they, especially with the wavelet data, those were the 2 data sets that had very nice separation of the probability distributions. So if you go back and look at that lecture, it's very nicely separated. And so what we're going to do is we're going to come over here and take the V matrix from the SVD, which tells us about that projection, and we're going to go take column 2, skip by 2 by 4. So this is going to pull out column 2 and 4. So okay, right, go to column 2, skip 2, go to 4. So go grab those 2 columns of data And this is the projection of the cat-dog data into modes 2 and 4 of the feature space. And those are the ones that seem to have the highest separability of the PDF. And what I'm going to do is basically build a Gaussian mixture models based upon those two features of the data. So mode 2 and 4 in the SVD modes, or PCA components 2 and 4. Okay? So here we're going to do. This is how easy it is. Fit GM distribution dog cat, which is what the 2-4 column, two probability distributions. And that comes back as GMM model. So that's it. So you just want to say, I'm going to fit it to two probability distributions. Go. And it's a Gaussian mixture model. So GMM means Gaussian mixture model. So I'm already assuming it's normally distributed variables, okay, with essentially two clusters. So if you do this, you're going to get out this model. And I'm going to plot the results of the model. But also, what's interesting about this GMM models, you can actually get out for yourself the AIC score. In other words, the IKEA information criteria will come right out of this. So it can tell you how good that model was. So this is really nice to have this built in as something that computes as it does it. So gmmodel.aic will give you back the AIC score for this fitting procedure. Okay? And so the rest of this is plotting. So I'm going to just show you this. The plots that this generates actually, they're viewed better in PowerPoint. So I'm going to go look at here. So once you run that fit, here's the kind of things you get. What I'm showing you here is the projection, the magenta and green balls are the projection into PCA space 2 and 4. Remember, those are the two features I extracted out of the V matrix and say, let's build a Gaussian mixture model based upon mode 2 and 4 projections, because when we looked at the histogram of those, they had nice separation. So again, that was out of lecture 5.1. And you can see it here. Again, dogs in magenta, cats in green. So what I've done is then I said, okay, take that data, fit two Gaussians. And there they are. So what I have is Gaussian 1, which has some mean and variance, Gaussian 2, which has another mean and variance. And these are the probability distributions associated with this. In fact, the contour lines here are the contour lines of this. And you can see the Gaussians do a good job in capturing a lot of the behavior you see here. In fact, what you get back is you get mu1, sigma 1, mu2, sigma 2. So you have those plus the weights alpha 1 and alpha 2. So you get that 6 parameters to describe this data in an unsupervised fashion. I did not tell it those were dogs and cats. I simply said, here's this data set with no labels. And what it tells you is there is, in fact, some Gaussian distribution of one of the data here plus another one there and runs through here. So again, unsupervised. All I gave it was the V2, the second column of V, fourth column of V, without labels. So that's very nice. I colored them in because I knew what they were. So that's another way to think about it. So what you would see is that maybe I would associate one with the other, and then there's a line of separation between them right here, and this is maybe where my decision line would be for classifying one type of data versus another type of data. But also now, since I have a probability distribution, I could also provide you with uncertainty metrics for this methodology, which is a very nice thing to be able to do when you make predictions of this sort, is to be able to say, well, you're down here in this tail of this distribution, the tail of that distribution. How certain am I that it's green versus magenta? And I have high uncertainty when I'm near this line, partly because I know that in there it could be either one, whereas I'm going to have very low uncertainty if I'm way out here. I'm pretty certain it's going to be magenta and not green, because now I have a probability distribution to associate every point with. Okay? So that's a nice result out of this Gaussian mixture model. The other thing it also gives you, I said that, is that if you looked, I had it plot out to the screen what the AIC score was. So it not only tells you these distributions, it also gives you some metric or some information criteria to evaluate that model. So now if I come back and try different models, you can start saying, well, if I have one model for the data, another model for the data, another model for the data. One thing you might want to do is say which model is the best. And normally what you do is you compute some kind of AIC, BIC score to evaluate how well they're doing relative to each other. And so that comes out for free out of this GMM mixture stuff. I want to highlight again, this is a really powerful technique. People use mixtures of Gaussians or mixture models all the time. And it's a very important method. In fact, the three that I highlighted in the book in section 5.3, 5.4, 5.5, right? So k-means, hierarchical, and mixture models. Those are sort of the workhorses of unsupervised learning. So you certainly need to be familiar with them. There are others, but those are sort of, they play a major role. They're sort of your go-to algorithms. When you have new data, like let's try something on it, these can give you information and can start getting you diagnostic features that you want out of your data to help you make informed decisions about the kind of data you have. All right, all the code. You can take this code, run it for yourself, play around with it, play around a little bit around with making more mixture models, having more clusters, less clusters, play with richer data sets. It's all here at databookuw.com. You can download all the code. There are a lot of more lectures. You can also download the PDF of the book here. So I encourage you to go poke around here and start looking at the suite of what we've covered so far, which are 3 of the most important unsupervised learning algorithms in use in practice in the community.